Okay, so let's start having a look at the alkenes then. First thing we notice is about the alkenes is that they have two p orbitals, one on each carbon, and that when these two p orbitals overlap sideways, they form a pi bond. The pi bond looks a bit more like this. So pi bond above and below the plane of this bond that's in the middle, that's the sigma bond, and then this is the pi bond. So one pi bond and one sigma bond between the two carbon atoms. And what we find is that that means that these two carbons can't rotate. There's no free rotation about this double bond. If we represent this in a slightly more normal looking model, what we see is something which looks more like this. So here we've got two lines, two sticks being used to represent the double bond. And what we see on this model is that again, the double bond does not rotate. So we can't get this type of 1,2-dichloroethene converting into this type of 1,2-dichloroethene. So we've got two distinctly different types of 1,2-dichloroethene, and we need to have an element to our nomenclature, system for our nomenclature, that enables us to identify which one's which. So let's now start trying to put some names to our different models of 1,2-dichloroethene we've got here. So this is 1,2-dichloroethene, and as we said before, the problem with this is we don't know whether the chlorines are on opposing sides of the double bond like this, or whether they're on the same side of the double bond like this model. And so our nomenclature needs to add in a small bit at the beginning of the name which enables us to identify which one's which. Now with 1,2-dichloroethene, this is relatively simple because what we've got is a situation where we've got the same group, in this case two chlorines or two hydrogens, on the same side or opposing sides of the double bond. So with this molecule, because we've got the same group either on the opposite sides or the same sides of the double bond, we can use a really simple piece of notation called cis-trans notation. And what we find is that if we use the word cis, it means that they are on the same side of the double bond. Or alternatively, we can use the word trans at the start of our name to indicate that they are on the opposite side of the double bond. So our model here of 1,2-dichloroethene with the chlorines on opposite sides of the double bond can be named trans 1,2-dichloroethene, and we just pop that bit of the name at the start, so trans goes in here, trans 1,2-dichloroethene. So far we've used cis-trans isomerism to notate whether or not isomers of alkenes are cis or trans, depending on whether or not the groups that they have are on the same side or opposing sides of the double bond. So for example, we said this was a trans isomer because the two chlorines, the two same groups, are on opposing sides of the double bond. Also, the hydrogens are on the opposing sides of the double bond as well. There is a second form of nomenclature, though, which we can use, and this is a slightly more advanced, more useful form of nomenclature in many ways, because what it does is it enables us to deal with some of the more complex examples, as we'll see in a minute. EZ nomenclature uses atomic numbers of elements to denote which elements are of highest priority. So to show you what I mean by that, chlorine here has an atomic number of 17, and hydrogen has an atomic number of 1. And what we do is we look at each of the two carbons individually, separately, and we see which of the elements coming off it has the highest priority, and the ones with the largest atomic number gain the highest priority. So in this case, that's the chlorine here, that has the highest priority on this carbon, and then on this side over here, the chlorine over here also has the highest priority. And we write either an E or a Z to denote whether or not the highest priority groups are on the same side or opposite sides of the double bond. So in this case, because they're on opposing sides of the double bond, this becomes an E isomer, and so we would call this E1,2-dichloroethene. So let's start looking at some slightly more complex examples. We have a look at a molecule here, 1-bromo, 2-chloro, 1-fluoroethene. And what we find is with this molecule that the cis-trans notation we've been using so far is of no use to us. We don't have two groups which are the same attached to both the carbons, so we can't apply a cis or a trans isomerism. Here, the EZ notation is the only one we can use. But we have a slight problem in the sense that we need to identify the atomic numbers associated with each element coming off the carbons before we can assign the priorities and ultimately assign E or Z notation. So let's have a little look at the atomic numbers of each of these elements here. So fluorine is a 9, bromine is a 35, and chlorine is a 17, and hydrogen is a 1. So having a look at this carbon on the left here, first of all, it's a 9 or a 35, so the bromine is of the highest priority. And looking at this side over here, we have a 17 and a 1, so it's the chlorine which is of the highest priority. In this case here, both of the high priority groups are on the same side of the double bond, so at that point we apply a Z to the beginning of our name, and this becomes a Z, 1-bromo, 2-chloro, 1-fluoroethene. So this example, we're going to use EZ nomenclature again to try and assign an E or a Z isomer to this particular alkene. The problem we've got though with this alkene is we notice that the carbon here is attached to two carbons. Now which one of these two carbons is the highest of the priorities is unclear, and the same with this carbon here, it's attached to two other carbons, so we've got the same problem there as well. All of these carbons have an atomic number of 6, so there's no difference. So what we need to do now is we need to involve our Cahn-Ingold-Prelog nomenclature, which essentially now allows us to separate and assign priorities to these carbons and therefore assign an E or a Z to our name. So let's have a look at what's attached to the carbon. So this carbon here is attached to 3 hydrogens, and what I'm going to do is I'm just going to write beside it the elements which are attached to that carbon in order of atomic number. So that's hydrogen, hydrogen, hydrogen for that carbon there. This carbon down here is attached to a carbon and is attached to 2 hydrogens, and again I'm just writing them down in atomic number order. This carbon up here is attached to 2 hydrogens and an oxygen. So again I'm going to write down the elements that it's attached to in atomic number order. This carbon down here is slightly more complicated because this carbon here is attached to 1 oxygen and it's attached to 1 hydrogen. There's only 2 elements coming off it because of the double bond. What we do is if we have a double bond like this is we count that element twice. So this one becomes oxygen, oxygen, hydrogen. What we do now is we have a look at each of the 2 groups coming off the carbons one at a time. So let's start with this carbon here, and we assign priorities based on the largest atomic numbers. So what we've got with this one is hydrogen, 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 and this one here we've got carbon, hydrogen, hydrogen. And because of the higher atomic number of the carbon, this one wins. So this group on this side is our highest priority group. Looking over this side here, we've got again a slightly more complex situation. We've got oxygen, hydrogen, hydrogen coming off it, and oxygen, oxygen, hydrogen. So in terms of the first element, they're both oxygens, they're both the same, no difference there. The second element though in this one here is a hydrogen, whereas the second element here in this one is an oxygen. Oxygen has an atomic number of 8, so it gains the higher priority. So this group here is our highest priority on this side. So both of the high priority groups being on the same side of the double bond means that we have ourselves a Z isomer. Okay, so at this stage you're probably thinking, right, well, is cis and Z essentially the same thing, and is trans and E essentially the same thing? Well, often they are. This is a cis isomer over here because we've got the same groups on the same sides of the double bond. And it's also a Z isomer as well because the highest priority group coming off this carbon, atomic number 17, is the same as the highest priority group coming off this carbon, again, atomic number 17. So that works. This molecule over here, again, it's a trans isomer because we've got the same groups. So we can use the cis-trans isomerism because we've got two of the same group. And again, it is a trans isomer because they're on opposing sides of the double bond. The E can be assigned also as well because the chlorines both have an atomic number of 17 and they're highest priority groups and they're on opposing sides of the double bond. So in this case, yes, cis is Z and trans is E. Unfortunately, things aren't always quite as simple as that. If we have a look at this molecule here, we see that whilst we've got two methyl groups here, and therefore this would be a cis isomer, so those two groups. If we start trying to apply EZ nomenclature to this, we come across some problems. So we've got a carbon here with an atomic number of 6, a carbon here with an atomic number of 6, a bromine up here with an atomic number of 35, and a hydrogen here with an atomic number of 1. And so if we apply the ideas of priority that we used before, then the 6, the 1, this methyl group here, the carbon, has the highest priority. If we apply the same ideas to the carbon and the bromine over here, we find that it's the bromine which gains the highest priority. So in this instance here, that whilst this is a cis, this is also an E isomer, as the highest priority groups are on opposite sides of the double bond. So to conclude, cis and trans are quite often associated with E and Z, but we need to be careful because they are not necessarily the same thing.